Okay, so I decided to talk about the thermal lensing initial LIGO for basically two reasons. For one, it was really the defining theme in basically the last year of commissioning of LIGO, and it was also the crucial step that we had, the crucial problem that we had to overcome to really get to design sensitivity. And secondly, I noticed that while there were plenty of talks about thermal compensation, thermal lensing out there already, there really was nothing that really covered everything. So that's kind of what I tried to do, to give an overview of all the issues in thermal lensing initial LIGO. Okay, I mean, for most of you, this slide is not really interesting anymore. This is my general LIGO slide. LIGO, three detectors at two sites, 10 milliseconds apart. Here's a picture of the Hanford detector. Houses two instruments. And a picture of the Livingston detectors. The buildings are really the same. The environment is definitely not. All right, here's a quick outline on what I want to touch on today. First of all, I want to show why and where thermal lensing is a problem in initial LIGO. And I want to give an overview of the hardware that was developed to tackle that problem. I go a little bit into the noise implications of that new hardware. I show the servo system that we had to implement to keep the interferometer running steady with this new hardware. I'll touch upon the limitations of this system, and this also leads over why we at the end still had to replace an optic. And finally, I have a slide on the current performance, and to conclude, a slide on the lessons that I think we should anticipate for advanced LIGO. All right, so why is thermal lensing a problem? To explain that, I want to start with the optical readout scheme that was chosen for initial LIGO. We phase modulate the input beam. That is then incident on the reflector port. We have first a recycling cavity consisting of the recycling mirror and the two input test masses. Both carrier and sideband fields are resonant in there. And finally, there are the arm cavities, which only the carrier field is resonant. At the dark port, then, the carrier is basically blocked out, hence the name, and only the sidebands are actually transmitted due to the Schnupp asymmetry, which is the difference in Lx and Ly. All right, so where is thermal lensing an issue? Well, you have the highest power in the arm cavity. So naively, the most power absorbed is on the input test masses and end test masses. However, the arm cavities have a G factor of about 0.3. That is, even though you change the radius of curvature a little bit, their optical modes really don't change that dramatically. This is different in the recycling cavity. This is basically a flat cavity that supports any mode, and any small change of the radius of curvature immediately affects the field. Strictly speaking, this is only in the recycling cavity is only true for the sideband because it doesn't see the arms. The carrier field, on the other hand, is defined by the arms, and this is also the mode that's supported in the recycling cavity. Now, here, that's exactly where we run into a problem. Since when we have lensing in this central part of the interferometer, thermal lenses, and it really doesn't matter in which optic it is because it's a flat cavity and there's basically no Gauge phase evolution. What happens is the sideband can change dramatically in size, while the carrier is defined by the arms and the input field, which is matched to the arms. Now, why is that bad? Well, the readout signal is the beat between carrier and sideband, and once you don't have a good overlap, your signal goes down, while you still get the shot noise contribution from the light that's in the dark port, so your signal to noise goes down. Moreover, if the supported field in the recycling cavity is not mode matched to the input beam, your coupling efficiencies goes down, so you lose twice. Well, this was, of course, all now known at the design phase, and the radius of curvatures of the optics were put into a shape such that for an anticipated amount of power and an anticipated amount of absorption, we should actually get the right configuration. Well, there's two problems with that. One, during initial commissioning, we were running at low power. Therefore, we didn't have the right curvature. And I'll show that actually led to a few troubles later on when the wavefront sensing system, the angular control system, actually had a few bugs that we had to take out. But more importantly, the absorption wasn't well known. So once we turned up the power, it turned out for one interferometer it was heating up too fast, for the others it was too slow. So bottom line is we really needed active control. So here's the description of short description of the hardware that was developed. Many people in this room actually worked on that too. So the system, the idea was if you can deposit heat on the ITM in a predefined shape, you can induce an additional lens. If you add more heat in the center, you can get a more convex lens. If you add heat in a ring pattern, you get the opposite effect. The way it was implemented is with a projection system that goes through a viewport into the vacuum. It's about 30 meters this distance. And in the image plane here, we can flip in different masks, either a central, either a ring mask or a mask with a hole in the middle. There's actually a little twist there, but that's basically the idea. There's one system for each input test mass, and the hope was with that we could just dial in the right amount of heat. There were several design considerations. One of the crucial ones, I would say, was the choice of the inner radius of the annulus. The kind of trade-off you had to do there was if the radius is too small, then the aberrations of your lens are growing fast as you go out. On the other hand, if it's too big, you're blocking out most of your power, and the total lens strength that you can achieve with the system goes down. So it's kind of an aberration versus maximum correction that you had to choose. Oops, that's the wrong direction. Here's a picture of the hardware for those who haven't seen it. It's the beam tube. Here is the optical table with a CO2 laser. There's a bunch of optics. The masks are about here, and then there's a projection system over a mirror and goes into the vacuum. The ITM is somewhere down here, 30 meters down there. Okay, so once we had that system installed, we did a few initial checks, and it worked just fine. This particular set of measurements was done with just a recycling cavity, and with an increased amount of heat deposited on the ITMs, we were able to affect the mode size at leisure. We found that at a certain amount of power we got the best match, and indeed that's where you want to run. From this state to this optimal state, you win about a factor of 2 in sideband recycling gain. And then with the full interferometer, this is a plot of the optical gain that you can achieve as a function of different heating state. So what I plotted here is normalized gain for different degrees of freedom. They're normalized to 1 at time equals 0. Then NBOB stands for normalized sideband power in the recycling cavity, and that's basically the green line here is to the power of 1, so that's the amount of sideband power you build up in the recycling cavity. Then at the AS port, that's your actual gravitational wave signal. You get a curve that scales roughly with the power of 0.8. You would expect 0.5 if it were just the amount of light, because you're proportional to the amplitude. So the additional factor is due to mode overlap. The effect is even more extreme on the pickoff port. There you get a scaling of about power to the 2.5, so you get an even bigger overlap effect there. Then there are 3 wavefront sensings, angular degree of freedom, that I also plotted. WOFS 2 is also in the pickoff beam, so it sees the same scaling as these auxiliary degrees of freedom. WOFS 4 actually uses a different sideband, so it's not affected at all. And the one oddity here was that wavefront sensor 1 actually went down. Now, it turns out that was because there was a mistake made when the wavefront sensor 1 GUI phase was installed. And that's kind of a typical thing that can happen if you start commissioning in a situation where your optical mode matching is not right yet. You start optimizing a system for the wrong type of fields, and turns out once the GUI phase was corrected for that, this WOFS 1 gain scaled the way it should, namely basically the same as wavefront sensor 1, as the dark port, as the red curve. All right. We just added a new system, so we have to worry about what this new system can do to our bottom line, our strain sensitivity. So this heat deposited on the optic, of course, doesn't only produce a lens, but it also changes the average optical thickness. And that's basically equivalent to a strain signal. Now, this transfer function, at DC, you get a constant gain. I'll come to that in the next slide. But at higher frequency, you get a roll-off due to a thermal pole, which is basically given by the amount of energy in the heated volume divided by the conductive cooling rate of that volume. And the relevant volume here is really just, this is half sphere of the volume of the beam at the surface. So it's just a piece of matter the size of the beam, not the whole optic. And that gives you a 1/f shape at higher frequencies. Here's the full-blown transfer function in theory. So it's the transfer function from relative intensity noise to displacement. The first term here, P over this expression down here, is basically the DC gain in temperature. That's the temperature change in this volume element that you affect. This is the frequency dependence with the thermal pole. And this is the change in the effective optical path length. It's just the size of the piece of matter that you heat up. And then there are 2 effects. The first is just from thermal expansion and change of the position of the surface. Is proportional to the thermal expansion coefficient times 1 plus epsilon, where epsilon is the Poisson ratio. That's just a geometrical constraint factor. And the other effect is the change of the index of refraction of the optic. And that effect is down by the finesse of the cavity, because you're not inside the Fabry-Perot cavity anymore. The bottom line is you get about 10 to the minus 16 meters per milliwatt of power onto the ITM at 150 Hertz. Now that was measured, and the agreement is actually too good to believe, given the rough derivation that we had. So 150 Hertz, 10 to the minus 16 is right here. The green and the blue curve are just two measurements for central heating. The two other curves down here are for analyst heating. There you get an additional geometry factor because you're not actually heating at the position of the beam. So the coupling actually goes down by roughly a factor of 10. That's about what you expect to.
Can you say again what this is? You're modulating the intensity of the thermal compensation at high frequencies, and seeing what the...
Yes.
Okay, so you actually see then a response in the gravity.
Basically, it's the same effect that we want to exploit at very low frequency. We want to change the optical thickness of the optic at different positions at the optic to form a lens. But the same effect is also there at high frequency. And any intensity noise fluctuation in your beam then affect your strain signal. And that's the transfer function for that. Okay, you can then make an estimate if you have an intensity noise stabilized CO2 laser. You can make an estimate that even for a high amount of correction power, we should actually have been good with a system like that. It shouldn't have affected us. We didn't have an intensity stabilized CO2 laser. So our intensity noise was actually worse, but we already ran into other trouble somewhere else. That's what I'm going to touch on in a couple of slides. So bottom line is, it actually worked. So we got about a factor of maybe 3 improvement in the shot noise regime due to the common TCS, the thermal compensation system action. But there was also a surprise. There was actually more than that, an additional improvement at high frequency, which was a reduction in the coupling of phase noise of the electronic oscillator that we used to produce the sidebands. Now, this coupling was always a little mysterious. The one thing that we're pretty sure about is that it's proportional to the sidebands imbalance times the carrier arm imbalance, reflectivity imbalance. Now, so basically, this is an experimental verification that this differential heating can affect this quantity. Unfortunately, there are definitely other misalignment types that can also affect this. So it's not, you can't necessarily reduce it to 0, but it's sure was a welcome improvement there. The last thing to notice there, that's already a year ago, that plot. So what was wrong with it? Well, that noise curve that you saw, we were able to manually tweak up, but then it really wasn't stable. After a time of about 30 minutes, the whole thing went to hell. So it became obvious after a while that we really were fighting another time constant, a slow one on the order of a couple of hours. And the question became, what is that time constant? First of all, experimentally, the way to fix such a slow drift is just to implement another servo. Now, to do that, you need error signals. You have 2 actuation points, so you need 2 error signals. First, the common error signal, X and Y in common. What you need is a signal that's linear across the point of maximum sideband recycling gain. Now, the best way to get a signal like that, because what you're actually doing is changing the mode size of the sideband, is you actually want a sensor that's sensitive to the mode matching of sideband and carrier. So in other words, you need a radial wavefront sensor, or another term for it is bullseye RF detector. And secondly, the differential error signal was kind of a lucky point that we already had a signal that we knew was sensitive to sideband imbalance temps, carrier arm imbalance, reflectivity imbalance, and there was always an annoying point because it's the orthogonal signal of our true signal, and we never had a way to actually reduce it, to reduce the nonlinearities in the mixers. So turned out just experimentally using that signal worked just fine for H1. It didn't work for L1. It's not 100% clear to me why not. However, as I said, there are other things that can produce the same type of signal other than the radial mode mismatch of sideband and carrier. So that might be the source of an explanation there. All right. Well, luckily, we already had a bullseye detector on shelf. Some guy back at the University of Florida, they had an undergraduate student that worked on that as his first project. And, well, there it was on the shelf, and we could use it. Well, thanks you, Florida. The installation was quite straightforward. The right point to install is in the pickoff beam, because that's where you have a sample of the two fields that you want to overlap. The mode size had to be such, the segment size, first of all, the way the diode looks, it has a center quadrant with a ring with a size of 1 millimeter, and then there's 3 additional quadrants in a ring around it. So you can actually take the difference between the center and the edge and get a mode matching signal from that. The size of the beam for a 1 millimeter radius diode has to be such that the first zero of the node of the first LIGO polynomial has to be right on that edge, which means the beam waist has to be about 1.4 millimeter. So that was straight. It was actually very welcome that the beam was that big, because it meant that we didn't need much of a telescope. We could just use a lens to focus it down, pick it quite a bit before the focal point, and didn't have any significant GUI phase evolution in that telescope. So we were basically in the right GUI phase to get the signal out. The mode shaping of the servo was straightforward. It was just a simple integrator and a compensation for the thermal pole. And with that, we got the instrument stable for at least 12 hours. There's usually another reason to lose lock after 12 hours. But the one thing you observed is that the required actuation actually increased by about a factor of 2 or so over that time. Again, that's that time constant that we're seeing. So the question is, why does the required actuation increase over time with this type of servo? We did some finite difference time domain modeling of that. So these are pictures of the temperature in an optic versus time at 0 seconds. This is the depth of the optic. This is the center. This is the edge. We put on an analogous heating pattern at the front, and then evolve in time after 750 seconds. You can see it propagates in. After about 5,000 seconds, it propagates in further, but because there is no cooling in the center, it also propagates to the center. And that actually leads to an effect that while you have a concave lens at the edge, as you go further in, the heat actually propagates to the center, and you get the opposite effect. So you get a kind of a sign flip of the effect as you propagate into the optic. This plot is just a plot of just that. It's the effective radius of curvature change per input power as a function of time that you shine on the optic. And you can see that you get a fast response on the order of this 10 minutes thermal pole, but then you get a slow drop-off of almost 50% with a time constant of about 4.3 hours. And the reason, as I said, is because the heat propagates into the center of the optic. With an impulse response of that model, I was able to compare that to the actual interferometer data. And for this plot, all I had to do is adjust the gain to match data and theory, and you can see that the match is pretty nice. Okay, moving on to the limitations of the thermal compensation system as it is installed. Well, as I have shown in an earlier slide, the thermal lens really isn't perfect. There are pretty strong aberrations, and they get stronger the more heat you put in. Now, here what I plot as a function of this overheating factor, which is nothing else than the power on the input on the optics divided by the power, the critical power, which is the power that we require for our optics to get to the best operating point. As a function of that ratio, I plot the power scattered out of the TM00 mode due to the aberrations in the thermal lens. And as a reference, the green line is what you get if you just use the cold state. You get a feeling for the size of the power that's scattered out. The second plot is just the required power. And the third is the relative correction. How much better you do by actually applying this thermal correction to just ignoring it, basically. And you can see that while it's very efficient in the beginning, there is really a flattening out because the thermal lens is really, the aberrations are becoming so big that you're losing so much power that's, in the end, you're still getting a lot of power out of the dark port that you don't want to. Now, on top of that, this theory was assuming a uniform absorption. So in practice, what we actually observed is not only did the amount of light get bigger at the dark port, but it also got a lot chunkier, which is kind of an indication that the absorption surface isn't uniform on your optic. And of course, with a system like that, you can't compensate that at all. So this realization really brought us to the conviction that we had to replace an optic. But then, which optic? I mean, this is a several $100 million project. When you open that up and have a downtime for a month, you want to know which optic is bad beforehand. So we had, okay, there are a whole bunch of, as I said in the first slide, there are basically the optics that we really care about in the central interferometer. We suspected that it's the ITMs because they see the high power in the arms, but we really weren't sure about that. So there basically were 3 different measurements that we were able to.
What's the relative effect of the role of the coating for the heat absorption and the lens itself? If you're applying some laser beam,
Yep.
and is the coating a super important factor in this? If you change the coating, would you change the effect of the heating?
Well, CO2 is chosen such that basically is nothing reflected on the optic. So the heating power is basically, most of it is absorbed. Is that what you're after, or?
Absorbed by the substrate.
By the substrate, yeah.
Go ahead.
It's absorbed by the substrate.
Right.
You're going in from the anti-reflective.
We're actually coming in from the HR side. That's just the geometry of the existing chambers. That's the only option.
In the HR code.
No, it's really not. The coating is not really relevant at this wavelength. It really gets all absorbed. It's a factor of 10 off in wavelengths.
Okay, that's really the question.
Yeah. Okay, so the first attempt to measure that was just run the system with the servo at different power levels and look at what your control signal gives you. Now this is a plot, power into the interferometer versus required correction power, and from the linear rise you can then conclude how much absorption you have. The problem with that method is you can't distinguish between beam splitter, RM, and the ITMs. The second method that Rick mainly and Malek came up with is a measurement of the transverse mode spacing in the arm cavities. This measurement is only sensitive to ETM and ITM and not to beam splitter and recycling mirror. And the idea here is if you misalign the cavity, you get higher order modes excited. Their frequency spacing is given by this formula and depends on the radius of curvature of the optic. So from that you can then conclude how much the radius of curvature has changed for an amount of power that you send into the optic. You can do that with the compensation system and with the interferometer and derive the absorption from that. And as usual, the most efficient measurement is the most simple one. And it took us a while to figure that out. If you just look at the spot size at the different ports, it actually depends on the lensing of the optic, because you have a simple telescope at the output. And you can just record the spot size at different ports over time as the optic cools down. And from that, you can again do that with a compensation system heating it up and with the interferometer heating it up, and can again derive absorption levels. The beauty of that is that we have several pickup ports, a dark port and reflective ports in principle, so you can really sample different passes through the interferometer and then invert that matrix and conclude which optics were really bad. So the bottom line of these, well, here are typical curves. These two curves were taken with a compensation system. It was heated up, and then here we broke the heat, and you can see the cool down. This is just the waist size of the spots. The top two were with the interferometer, and from the ratio you can then figure out what the absorption is. Well, the absorption was bad, about 15 times worse than it should have been. These are the values that we finally came up with. And also important, there was really nothing wrong with beam splitter and recycling mirror that we would care about. So at that point, actually to be precise, at that point we weren't 100% sure whether it was in the coating or in the bulk. It seemed more likely to be in the coating because you only had to be 15 times worse than spec. While in the bulk, it had to be more than 100 times worse than spec. But since we know what optics were bad, the vacuum was broken on June 30th. ITMX was replaced. ITMY drag wiped, and both of which turned out to have a very positive effect. The same measurement afterwards constrained the absorption to less than 1.3 ppm. So we knew we got rid of that problem. And kind of a funny turn is that the TCS is still required, but in the other mode. We really don't get the interferometer hot enough now after the optic was changed without the TCS system. So here's a slide. It's basically just another calibration spectrum that I took from the E-log about the current performance. The February 1st curve was still with the old optic that was just before S4, if I remember right. And you can see the improvement in the shot noise regime is about maybe a factor of 2. And there are two effects that contributed to that. We were able to run at 50% more power, but that only explains like square root of that in sensitivity. On top of that, you really got less chunk out of the dartboard. The picture at the dartboard really looks nicer with the new optic. So these two effects together allowed us to basically bring the interferometer to a state like that, and that's basically where it's running at now. Basically at design sensitivity. All right, so to conclude, this is kind of my take of what we should take away from that. First of all, the whole problem with this lensing just was due to this, our specific choice of the readout systems. So if what is intended to be chosen for advanced LIGO, the DC readout scheme, we wouldn't have been affected by that at all. We kind of wouldn't care. Secondly, it really seems important to me that when we start commissioning, we already make sure that the mode matching in the interferometer is correct, basically in the state that we want to be in. Because otherwise you tune your angular alignment system to the wrong fields, and it's almost guaranteed that you have to redo that afterwards once you go up in power. And there's two ways to do that. Either you put in a thermal compensation system that can do all the load a priori for you, or you could imagine compensation plates that you put in for low power operation, and so you don't have to worry about all that at low power. And then later on, once you know how much you absorb, you design a second set of compensation plates and put that in, and are already in the right regime, and then you only have to fine-tune it. And yeah, point design really didn't work out for initial LIGO. Third, it's really a lot easier to just add a little more heat in the center than to heat up the whole optic except for a little point in the center. So however you want to do it, it's certainly easier if you go to that side and then tweak it up. And finally, the time dependence is also important. And for initial LIGO, the main time constant between a lock acquisition and actually ready for data taking is now just the time constant the servo takes to bring us in. It's on the order of 10 minutes. If we don't have a servo, it would even be longer than that. Yeah, I think that's about all I had.